Hello friends. So today we are going to discuss three questions that were asked in the year 1993, 1991 and 1988. So in the first one, which were asked in the year 1993, it is given that a rectangular frame ABCD made of a uniform metal wire has a straight connection between E and F made of same wire as shown in the figure. AEFD is a square of side 1 meter and EB is equal to FC each 0.5 meter. The entire circuit is placed in a steadily increasing uniform magnetic field directed into the plane of the paper and normal to it. The rate of change of magnetic field is 1 Tesla per second. The resistance per unit length of the wire is 1 ohm. Okay, so this should be ohm, not watt. Find the magnitudes and the direction of the currents in the segments AE, BE and EF. So we are given this diagram. So we have a square A, B, C, D and we have magnetic field which is directly into the paper. And separately A, E and F are joined and it is given that their respective length are given. So we are given that AEFD is a square of side 1 meter. So this is each is 1 meter and this is 0.5. This will be also 1 meter. And we are given that a rate of change of magnetic field which is into the paper is given as 1 Tesla per second. So here we have dB by dt is equal to 1 Tesla per second, and it is also given that the resistance per unit length of the wire is 1 ohm per meter. Okay. So you can say resistance per unit length resistance per unit length is 1 ohm per meter. And in this case, as the magnetic field is increasing, or we can say the entire loop ABCD is placed inside a uniformly increasing magnetic field. So because of that, according to Lenz's law, the induced current will be flowing inside this loop, and that is going to oppose this increasing magnetic field. So therefore, the induced current will try to create a magnetic field which will be out of the paper. So we can draw here a conclusion from there. We can say that loop is placed inside, we can say loop is placed in a, not inside, placed in a uniformly increasing magnetic field. Uniformly increasing magnetic field, and which is directed into the paper. Directed into the paper. So because of that, according to 𝑨𝑬𝑪 law, according to 𝑨𝑬𝑪 law, the induced current will flow in such a way that opposes the change in magnetic flux, or we can say that flow in such a way that opposes change in magnetic flux. And we are given that since the magnetic field is increasing into the paper, the induced current will try to create a magnetic field out of the paper. Will try to create magnetic field out of the paper. Okay. And because of this, we are going to have induced EMF. So let us calculate the induced EMF of both the loops. So we have induced EMF. So let us calculate, and for this we are going to use E is equal to minus d phi by dt. So we can represent the magnetic field. Phi b is our magnetic field multiplied by area. So this becomes d of dt b upon a. And here a is constant, whereas magnetic field is changing. We can say the induced EMF will be equal to minus a dB by dt. We are going to use this formula in the respective loops. So we write for loop AEF D, which is 1 by 1 meter. So we get induced EMF in the loop AEF D is equal to minus of 1 into 1, and rate of increase is given as 1. So this comes as of minus 1 volt. And then is our second loop, which is loop of EBCF, and that is of 0.5 into 1. So we get induced EMF in EBCF will be equal to minus 0.5 into 1 into 1. This gives us minus 0.5 volts. So based on this, we can draw the respective circuit, modified circuit rather, which shows the position of the induced EMF. Okay, let us calculate the respective resistances also. So here we are given that the resistance is 1 ohm per meter. Okay. So let us find out the resistances of respective arms. Resistances of respective arms, and because the increase in resistance or change in resistance is 1 ohm per meter, so it means if you find out the resistance of the loop, which is having 4 sides, so each side is going to have an equal resistance. So based on this, we can say for our loop AEFD, we have resistance will be equal to AEFD will be equal to 1 plus 1 plus 1 plus 1, and this comes as 4 ohm. So therefore, for each side of loop AEFD, we are going to have 1 ohm resistance. And next is our loop EBCF. So we can say resistance of EBCF will be equal to, here it becomes as 0.5 plus 1, 0.5 plus 1, and this gives us, sorry, here I forgot to multiply by 1. Multiply by 1 because it is given as 1 meter, and this comes as 3 ohm. So here you can say that the resistance of each side will be 1 ohm. Each side for loop EBCF will be equal to 1 ohm, because one side will be common to both the loops. So therefore, this 3 will be divided only into 3 parts. So based on this, we can draw the diagram. Now we can write it as a resistor network, and we are going to have this as this is a resistor network. Each resistance is of 1 ohm, and the voltage EMF, that is, this will be 1 ohm, and here it will be 0.5 volt, and the currents that were flowing, this is our A, B, C and D, and here we have E and F. So we say current, let this current be our I1, and this current is I2. So from here we are going to have current I1 minus I2, and the magnetic field is into the loop, and which is changing by the rate which is given to us. So we have 2 loops. So in these 2 loops we are going to use Kirchhoff voltage law, and find out the value of the current. Applying KVL, so our first loop is AEFD. So in this case, we can write minus of 1 plus minus 1 plus I1, and this comes plus minus 1, sorry, multiply by I1, and here we have this loop. We have current I1 minus I2, so this comes as minus 1 into I1 minus I2, and then we come here, this comes as plus minus 1, sorry, once again, multiply by I1 is equal to 0. So this gives us equation 1, which is our 4I1 minus I2 is equal to 1. Let be equation number 1, and this equation number 1, now we can use our second loop, and in this second loop it is given that we have looped this as EBCF. You can say loop EBCF, and in this loop we can write the equation will be our 0.5 minus it has to be plus 1 into I2 plus minus 1 into I1 minus I2, and then it comes plus 0.5 into I1 is equal to 0. So this gives an equation that minus I1 plus 3I2 is equal to 0.5. So this is equation number second. So using equation 1 and 2, these are two simultaneous equations. Using equation 1 and 2, we can easily solve them, and we get from here that our, let me write the results directly. So we are going to get that our I1 will be equal to 7 upon 22 ampere, and we have I2 will be equal to 6 upon 22 ampere. And so our I1, and also we need a current I1 minus I2 because that current is flowing through loop EF. So therefore, we can write that our IEF, which is I1 minus I2, so this comes as 7 upon 22 minus 6 upon 22 is equal to 1 upon 22 ampere. So therefore, we found out the current in each loop. So this 7.22 is the current in the loop current in the side, that is IAE, and this I2 will be equal to IBE. So we found out all the three currents which we are supposed to, magnitude we already found out. So this completes the first question. Now we come to the second question, which was asked in the year 1991, and here it is said that a circuit containing two position switch S as shown in figure. So this is the figure. We have two position switch S. In the first instant, based on this, it is connected to position 1 and then it is switched to position number 2. So based on this, we have these two broader questions, and part B has two sub questions. In question number A, it is given that the switch S is in position 1. Find the potential difference VA minus VB and the rate of production of the joule heat in R1. And for part B, it's given that the switch is put in position 2 at t is equal to 0. Find the steady current in R4. The time when current in R4 is half the stated value. Also calculate the energy stored in inductor L at that time. So we are going to discuss part A when the switch is in position 1. Position 1, and which can be also said that it is a steady state analysis. Steady state analysis. Now here we can see that when the switch is connected to position 1, there is a capacitor which will be coming into the picture, and at steady state the capacitor acts as an open circuit. Okay, so this capacitor will be acting as an open circuit under steady state condition when A is connected to 1. Okay. So we can write that at steady state the capacitor acts as an open circuit. Open circuit. Okay. So which basically means no current flows through it. Therefore, we can draw this circuit a little bit in the modified form, and this can be drawn as we have a resistance here, and this resistance is given as R3, and here we have the capacitor which will be now acting as open circuit, and we have resistance R1 which is connected to a battery source which is our E1. So we have R1 and we have E1, and to the other end of the capacitor we have resistance which is our R5, and here it is have 1 ohm. Now the switch is connected to position number 1, so this is position number 1 and this is our switch, and here we have point A, another battery source which is connected to a series of resistance that is of R2, and other end is called as B, and this will be our initial circuit. So this is given as E2. So from here we can clearly see that there is open circuit with respect to the capacitor. So as there is open circuit with respect to capacitor, no current will be flowing through the capacitor. So let us assume that from E2 current I1 is flowing. So at this point it will try to divide itself into two parts. along this way, along R5 and along this way. But as we have an open circuit here, so no current will be flowing in this direction. So here we are going to have current I1. Here it will try to divide itself into two parts. So let us suppose in this direction we have I2. So therefore through E1 we have current I1 minus I2. So here we have two loops. Let us call this as loop number 1 and this as our loop number 2. So we have two loops. We are going to use KVL in both the loops. And this will be giving us the value of the respective currents because we have two unknowns. So these two unknowns are I1 and I2. And this will help in finding out the value of I1 and I2. Okay. So you can see applying KVL. In loop 1, so we can write that minus of 2I2 plus 2 I1 minus I2 plus 12 is equal to 0. And for the simplification of this, we are going to get one equation. We can write that I1 minus twice I2 is equal to minus of 6. Let this be equation number 1. Now we come to the loop 2. And in loop 2, we can write the equation as minus of 12 minus 2 I1 minus I2 plus 3 minus 2I2 is equal to 0. And its simplification gives us 4I1 minus 2I2 is equal to minus of 9. This is equation number 2. Now if these are two simultaneous equations, so solving 1 and 2, using equation 1 and 2, we get I1 will be equal to minus 1 ampere and our I2 will be equal to 2.5 amperes. So we were able to find out I1 and I2, and in the first part it is said that the potential difference VA minus VB. So let this be our VA and this will be our VB, and here the only current that is will be our interest is our I1 because that is only flowing through this and going to affect the potential difference VA and VB, VA minus VB rather. So we are going to find out what will be the potential drop across this R2. So we can write that potential difference which is our, for that we can write the equation, and that will be our VA plus 3 minus 2I1 is equal to our VB. And we need to find out VA minus VB. So this becomes VA minus VB is equal to 2 minus 1, substitute the value 3, and this comes as minus of 5 volt. So this is the potential difference across our R2, or we can say VA minus VB. We are also supposed to find out the power dissipated in R1. So we can write this as PR1 is equal to I1 minus I2 whole square multiplied by R1 minus 1 minus 2.5 whole square and multiply by 2. So from here you get power dissipated in R1 will be equal to 24.5 watts. So this was our first part, A part rather. Now in the B part, it says that the position is now switched to position number 2. So let us draw the circuit for our B part. Switch position is true, and here, like in first case we did a steady state analysis, the position number 2 gives us a transient analysis. So we can just modify our circuit. So we have this voltage source and a resistance connected in series. This is our switch. Now switch is connected to point 2, and across this we have inductor, and here we have a resistance. So we have, this is 2 ohm, this is our 3 ohm, inductor of our 10 millihenry, and a voltage source of 3 volt. Now this ultimately comes as series RL circuit, and here R will be our R equivalent, the combination of 2 ohm as well as 3 ohm. So first of all, let us find out the steady state current. Steady state current. So at steady state, our inductor will be acting as short circuit. Inductor will be our short circuit. Therefore, the only values which will be affecting the value of the current will be the combination of the resistance 2 ohm as well as 3 ohm. So let us call that steady state current as I naught. So we can say our I naught will be equal to the voltage divided by R equivalent. So voltage our 3, and here we have 3 plus 2, and this gives us 3 divided by 5, which comes close to as 0.6 amperes. And it is asked that time for the current to reach half of its steady state value. Time for the current to reach half of its steady state value. And we know the equation that the current through inductor follows a exponential growth. So we can write the equation based on this. We can say the current through inductor follows the exponential growth equation. The exponential growth equation, and we can write this as our I is equal to I naught 1 minus E, and this comes as minus T upon tau. Here tau is our time constant. Tau is our time constant, and it is said that I should be I naught by 2, half of the steady state value. can say, but I is equal to I naught by 2. So we can modify the equation. We get I naught by 2 is equal to I naught 1 minus E minus T upon tau. Here I naught and I naught cancels out, and we get this as by 2 is equal to 1 minus E minus T upon tau. Now it's quite simple now. You can write this as E minus T upon tau is equal to 1.2, and just solve it. We get this as minus T upon tau will be equal to natural log of 0.5, and let me write it other way. So this can be written as minus T upon tau is giving us minus natural log of 2. So this minus and minus cancels out. So we get from here that our T is equal to tau and natural log of 2. We can find out our value of tau, which is our time constant, that will be equal to L upon R. Here R will be our R equivalent. So if this is 10 into 10 to the power minus 3, R equivalent will be our 2 plus 3. Yeah, 2 plus 3. And this comes as close to 2 into 10 to the power minus 3 seconds. So therefore we get T is equal to 2 into 10 to the power minus 3, and natural log of 2 is given as 0.693. So this gives us T is equal to 1.386 into 10 to the power minus 3 seconds. So this was our first part, and we also said that we found out the steady state current, we found out the current half the steady state value, and we are going to find out the energy at that time. Okay. So we find out the energy in the inductor. Energy stored in inductor, and we already know this formula, which is U is equal to half Li square. Let's simply substitute value. We get our U is equal to half, inductor is our 10 into 10 to the power minus 3, and value of current is 0.3 and its whole square. So this energy will be coming as 4.5 into 10 to the power minus 4 joules. So this completes our second question. And in the third question, which was asked in the year 1998, and it is given that the two long parallel horizontal rails, distance d apart, each having a resistance lambda per unit length, are joined at one end by a resistance R. A perfect conducting rod Mn of mass m is free to slide along the rails without friction. There is a uniform magnetic field of induction B normal to the plane of the paper and directed into the paper. A variable force F is applied to the rod Mn such that the rod moves, a constant current I flows through R. So based on this question, description, we have two questions. Find the velocity of the rod and the applied force F as a function of distance x of the rod from R multiplied by velocity v. Second part, the fraction of work done per second is converted into heat. So we are given this circuit, we have a rod Mn which is free to slide, and a force is applied to the right side. So it is moving with the velocity v towards the right, and we have magnetic field which is into the paper, and the loop is connected to the resistance R. So as the force F is being applied and the rod is moving towards left, so there will be induced EMF across the rod. So you can see that the induced EMF across the rod and that can be written as E is equal to BV multiplied by D. So D is the length of the rod, and it's also given that the resistance is horizontal rails are having a resistance of lambda per unit length. So we have these horizontal rails, and the rails are going to have a resistance of lambda per unit length. Therefore, at any instant when the rod is at a distance of x from one end, then we can say the resistance of this entire rod will be equal to lambda x, and to the other end also we are going to have a resistance of lambda x. Okay, so we can just remodify the circuit and we can draw a little bit of resistance part here. So we are going to have upper part is going to have resistance and lower part is also going to have resistance, and this is under the condition that the rod is at a distance of x from one end. Therefore we are going to have this as a lambda x, and this will be also our lambda x, and we have a resistance of given, that is our R. So now, and this is our rod. So we can find out the total resistance of the circuit. So in this case, we say that for the rod to be at a distance x at any instant, the total resistance in the network or we can call it as a circuit, not a network. In the circuit, let us call that as RT, which will go R plus lambda x and plus lambda x. This gives us R plus 2 lambda x. So now we can use simple our Ohm's law to find out the current in the circuit. So we can say current in the circuit, which will be given as I is equal to E upon R. Induced EMF we already know is our BVD, and this R is in this case of total resistance RT, and this we found out is R plus twice lambda multiplied by x. Now we can find out the value of x from this particular equation, or rather we can say the velocity as a function of time. We can say the velocity of rod as a function of time velocity of rod as a function of time.
Okay, I found this on the...
Sorry about that. Velocity as a function of time, and in this case we can say that our velocity so we have that the rod is moving towards right side, and we have magnetic field which is directed into the paper. So because of this there will be a force acting because of this, or sorry, and so we have a rod moving towards right with the velocity v, and because of this there will be induced current in this rod and induced voltage, which will be creating a magnetic field, and because of this we are going to experience a force, or rather we can say rod will be experiencing force in the opposite direction. That will be our FP, and we know that our FP is equal to EL multiply, sorry, is our BLV. B here, L is the length which is given as T multiplied by V. Therefore, we can write that the velocity as a function of time, it can be written as, if we modify this equation, we can get V is equal to our FP divided by BLV. And this velocity is our dx upon dt. This gives us our force because of magnetic field, and here we have, sorry, it is d, not L, d. And we already know, yeah, so therefore we can write this equation as V is equal to, not V, or we can say V is our dx by dt, which gives us into I, and here comes our R plus 2 lambda time x divided by BD. Now we can find out the instantaneous acceleration. We can simply derivate it once more. We get instantaneous acceleration A will be equal to double derivative of x, and we can say our acceleration is equal to this will be our 2I lambda BD, and we substitute the value, becomes I R plus 2 lambda x divided by BD. So we get this as acceleration is equal to we get this as 2 I square, we have this lambda, and this is our R plus 2 lambda times x divided by b square and d square. So this is our acceleration A, which is another form can be represented as, you can say, double derivative of distance x. Next, we are supposed to find out the instantaneous applied force. We found out our acceleration, then we can find out the instantaneous applied force. instantaneous applied force, which is F is equal to mass into acceleration. So we get F is equal to m, and we found out acceleration will be our 2I square lambda r plus 2 lambda times x divided by b square and d square. And in the part B, we are supposed to find out the fraction of work done converted to heat. And our heat is given as I square. Okay, heat is required to find out per square T. So we are going to get it as I square R. So we can write heat produced per second. Heat produced per second. H will be our I square R. And here time is 1 second. So there is no need to write this T, and this R is our R total, which we just found out. And we can write our H is equal to I square, and this R is our RT is our R plus 2 lambda times X. And we can say that our 1 second. Yeah, we already know the current. And the next we are going to find out the power. So we can say our power is equal to, so not power but fraction of work done. Okay, so we can say work done W will equal to force, and multiply by, we have R, and this comes our R plus 2 lambda X divided by BD. And we have to find out the fraction. So therefore you can say that our heat produced divided by work done will be over H upon W, and this gives us H we found out is our I square R plus 2 lambda X, and divided by, here we have F into I, and this is our R plus 2 lambda X divided by BD. This is our the ratio of heat produced to the work done. So these were the 3 questions asked in the year 1993, 1991 and 1998. So these completes the 3 questions. Thank you.